Okay, so now we're going to look at what happens when we want to transform the basic trig function. So that's sine, cos, and tan. And depending on where we change the value in the equation, it'll have a different effect on the graph, and then we'll summarize what this all means at the end. Okay, something to note obviously is that we can do one more transformation, which is not covered in this syllabus, and that is actually to add a value here, right? That's a horizontal shift, which we're not going to look at this year. So we're not looking at this transformation here. All right, so what we're going to do is we're going to switch to Desmos in order for us to understand what happens when we change the values what happens when we change the values depending on where these values are. So let's start off with the basic sine graph. All right, so here we have a standard sine graph. As you can see, it starts at 0, rises to 90 at 1, down to 180, 0, and finishes at 360 degrees. So the first transformation we're going to look at is what happens when we change the value in front of the sine itself, right? So this is the a in my equation, and when we change this value, if we increase the value, what's going to happen is the height, or the minimum or the maximum points of this graph, are going to change proportionately. So as I increase the value of this number is going to increase. And so it's acting as a stretch in that vertical direction. So as I increase the value, the height of the minimum and maximum points are increasing, and obviously as I lessen this value, it is decreasing, right? So in trigonometry, the A, right, actually stands for amplitude, right? So this is the amplitude of a sinusoidal wave. As you increase it, you increase the height and the minimum point as well. All right, let's look at the next value. And the next value is the number in front of x itself, right? This is going to cause a horizontal skew or stretch, right? And remember, horizontal stretches are 1 over the value. So as I increase the value, the graph is actually going to push in slightly. So if I move this over to 2, you'll notice that the graph is starting to push in. Now, another way of thinking about this is this value increases the frequency of the graph. Okay, so I've pushed this number to 2, and what's happened is within 360 degrees, I now have 2 copies of the same graph. If I had to push this to 3, you'll notice that within the 360 degrees of the original graph, I now have 3 copies of the same graph. Alternatively, how you could think about this is how it affects the period, okay? So sine generally has a period of 360 degrees. And if I take the general period and I divide it by the number in front of x, it will tell me how much the period has become now. So 360 divided by 3 is 120, and you'll notice that it now only takes 120 degrees for one sine graph to complete a full copy. So period and frequency are basically the same concept, just viewed at different angles. Okay, so frequency tells you how many copies you'll have in the normal period, and period tells you how long the period of the sine graph or the other graph is now, right? Based off the original. The original being the standard sine function where the period is 1, and we know that the period of sine is 360 degrees. Okay, the final thing we're going to look at is c, which sits outside of the sine function, right? And all this is going to do, like we know from other graphs, is it's just a vertical shift. So if I increase the value for c, the graph will shift up. And if I decrease the value for c, the graph will shift down, right? And it's important to note that vertical shifts always happen last, okay? Because they are the furthest thing away from our variables. So we would apply the amplitude and the period change first, and the vertical shift is the last thing that would be affected. Okay, so if there's no vertical shift, it's the standard sine graph, and as I increase, the graph would just move up and move down with exactly the same number of units that I put in C. Okay, so this is just a translation, a vertical translation. Now, when we move from sine to cos, we find that we have exactly the same effect. So the number in front just affects the amplitude. So as I increase this value, the amplitude, right? So the difference from, or the height from the center of the graph to the maximum and from the center to the minimum is increasing by that value or decreasing. And if I change the number in front of x, the frequency of the period, if I increase the number, obviously the frequency is going to increase, which means we're going to have more copies of the graph within the same period. Or another way of thinking about it is we're going to decrease the period. Okay, so we have the period of the cosine graph is now less, right? It's 360 degrees divided by 2, which means that it only takes 180 degrees for a full copy of the sine graph or the cosine graph to appear. Now, we can also look at what happens when we go to values less than 1. This is obviously, say, for instance, a half. This now means that the frequency is a half, meaning that we only have half a sine graph in the normal period of 360 degrees. Alternatively, we could take the normal period, which is 360 degrees, and divide it by half, and this will give us 720 degrees. This tells us that it will take 720 degrees for us to get a full copy of the sine or the cosine graph in this case. All right, let's move that back to 1. And once again, like before, this is just going, the C is just going to be a vertical shift up or down depending on the value of C. Okay, let's look at the final graph, which is tan. Right, now tan is slightly different to the other two graphs in the sense that if we have a look at the value for A, sine doesn't really have an amplitude, right? Because of its nature, it's not really affected as much by amplitude as, or it doesn't have a maximum or minimum amplitude, right? And so it doesn't behave in exactly the same way, right? What we will do is we will track the value of sine at 45 degrees. That's generally a good place to look at what the amplitude is doing. And in the same way as the previous graphs, if we increase the value for B, we increase the frequency. So if we increase the frequency for tan to 2, that now means that we have twice as many tan graphs within 360 degrees. And remember, tan is only taking 180 degrees to repeat itself, which means we're now actually going to have 4 copies. And similarly to the other two, if we increase the value for C, it's just going to shift the graph up and down depending on the value for C. All right, and it actually might be easier if I went back to 0 or 1 here, and we're just shifting up and shifting down, right? And this is just a bit of an optical illusion, but this is actually just shifting up and down. So let's summarize what we've just seen, okay? So A is the amplitude. It's going to tell us the maximum or minimum value of the graph, right? Remembering that the normal sine graph is from at 1, the amplitude in front, or the number in front of sine, or A, will tell us what the new maximum or minimum value would be, right? Then we have B, which is, you can either think of the frequency, right? This is how many copies of the regular sine graph. Alternatively, you can think of this as period, right? Period telling us how long does it take for the graph to complete a full cycle, right? and remembering that the full cycle of the normal sine graph at 360 degrees, if you divide that by b, it will tell you the new period. Okay, so there's two ways to think about that. And c, this is just a translation. It's just a shift vertically up or down. And in the same sense, we looked at cos and we saw that this also happened to be a change in amplitude. Right? The number in front of cos will change its amplitude. What is the difference between the center of the graph to its maximum point and to its minimum point? Okay, now remember, it's not going to tell you the maximum and minimum point, because if we have a vertical shift in as well, the maximum and minimum values will also shift depending on the value of c, but it will tell you, A will tell you the height from the center of the cos graph to its maximum value and from the center down to its minimum value. Right, B again is our frequency. Right, how often are we going to get one copy of the cos graph in its normal cycle, which is 360 degrees, or we can think about it as period. And once again, cos has a period of 360 degrees. If we divide that by b, it'll tell us what the new period is. And then c is just a translation again. And all it does is it tells us how much the graph is translated up or down. And then finally we had y equal to tan, all right, when we shift tan around. Now, tan doesn't have an amplitude, so we can sort of just think of this as a stretch. Right? There's no maximum or minimum value for tan because they can go on to positive and negative infinity. However, we can still determine the frequency of tan, so how many copies of the tan graph based on what it normally is. Alternatively, it tells us the period, but we must remember that the period of tan is actually only 180 degrees, and if we divide that by b, it'll tell us the new frequency. And the important thing to note with tan is we also need to remember that the asymptotes, so if we go back to the original tan graph, if we change the frequency, we will also change the frequency or the period of the asymptotes as well, right? And finally, we have C. Again, it's just a translation, and it'll tell us how much the graph is shifting up or down. Now, other than that, those are the only three transformations that we're going to be looking at for these three graphs this year. And what you might have noticed is that two of them affect the transformations, and one of them is a horizontal transformation. And it's very important then when we have more than one transformation happening at the same time in the same dimension, so vertical or horizontal, that we know which one to apply first. So when it comes to the vertical transformations, we always do the amplitude first and then the vertical shift. And the reason that we do the amplitude first is you'll notice that the amplitude is closer connected to our cos of x, and the vertical transformation kind of happens afterwards. So we always treat the amplitude change first, and then we apply the vertical shift. If you do it in the opposite order, you're going to get a very weird looking graph.